Hello everybody and welcome to a new video. So in this one we are going to see how to recreate the effect called volumetric light scattering as it is explained in the GPU Gems book number 3. Okay, amazing. So as you can see, I got here this little model of a house, kind of a hobbit house because of the round door and windows. And here there is our light, which has these rays, which are also often called God rays, or in general volumetric light. This is a post-processing effect, which means the effect is applied only on the final texture that we get out of our node. This is not an effect created using vertices or creating additional polygons. This is just an effect that happens inside the GPU completely, inside our final texture. So the cool thing about this technique is that it recreates the rays of light like if it would be a very bright light that scatter inside the atmosphere because of, I don't know, particles of humidity in the air and so on. So it's a very nice effect to give a feeling of reality to the scene. You can also change the color of the light. I like very much also to make it very small, that it almost disappears. And then to make it bigger. So it's a pretty cool effect, and we're going to see in this video how this works. So we will start really from scratch. And what we need is of course a JIT world with a camera, why not? Let me first say that probably we will not manage to do this all in one video. It's probably going to be a series of a couple of videos, but let's see where we arrive with this one. So then we need of course an object to in our scene. Let's create a GGL grid shape that draws to, actually will draw to a node. So let's give it already the name of the node. Let's call it node. And let's give it a shape, a sphere, and so on. What is important is to give a color, for example, of white, but an alpha of 0. So why an alpha of 0? We are going to see that as soon as we understand what's going on. Cool. Then we will need a node, because as we say, this is an effect that is entirely done in a GPU on a texture level, so it's a post-processing effect. So we need to capture the whole scene into a texture, so let's create a node for that. Let's give it the name node, capture 1, and let's give it full scale, anti-aliasing, let's give it erase color, I don't know, let's erase the, doesn't matter, we will just erase the color using a swatch. So let's create a swatch, and let's say prepend erase color. Cool. Then let's create a GGL video plane, which draws to game, transform reset to. Great. So here we got our sphere and the background of our scene. Great. We probably want to shade the sphere, but we are going to do this in a second with a GGL material or something. Good. So another thing we need is a light, so let's create actually another grid shape. Let's give it a color of, I don't know, like yellow, and scale it pretty small. And let's actually put this somewhere else. So let's say pack position FFF. And we're going to move this light a bit around in the scene. So it's, I call it light, but it's actually just a normal sphere. Cool. So there is our little light there. Then let's create also a real light, so an OpenGL light. So GGL light, which draws to game, because it cannot draw to node. Lights are not allowed to draw to nodes. Or maybe yes, last time I checked it was not possible. Maybe now it's possible. So let's give it as a diffuse color, the same color we gave to the grid shape. Cool, let's check if this actually worked by enabling the light. Okay, cool. Let's put them on the same position. And let's give it also the type point. So, great. Exactly. So basically this this little sphere here represents a point light that illuminates our scene. Okay, great. Then what we need now is kind of the meat of our algorithm. it is a GGL slab. So GGL slab node. It's going to have two inputs, so let's specify it, inputs 2, and it's going to get a shader file, so let's actually give it a file, volumetric light.gxs. Cool, this file doesn't exist, in fact you cannot find it. So let's open it. So this is the default shader, let's save it onto the desktop. So volumetric light, not tooth, but JXS. So let's save this into the desktop. Cool. So now this should be buff on the desktop. Exactly. So if we reload, if we recreate this object, it should now contain the file. Great. Let's actually open this this shader with Visual Studio Code or whatever editor you prefer, just to have a better highlighting and in general a better editing experience of this shader. So cool, so this is the default shader, right? Great, so let me briefly explain you how this algorithm works. So we got the light position here. Now if the light is not covered by an object, every pixel in our final rendering image is going to send a vector to this to the center of this light, and then the light is going to be resampled, so the image containing the light is going to be resampled in a radial way, so going always farther and farther, and this gives us the impression of rays emerging out from the light. So I made you a little image, there it is. So this is going to be our light position, and these are the pixels of our final image, and every pixel is going to send a vector to this light a certain number of times, from 200 to 400 depending on your GPU, because more times you do this, the algorithm becomes heavier and heavier. So the more times you do this, the better result you will have, because we will basically sum together all these rays and have in the end the final color of the rays. So this is how the algorithm works. It's actually very, very easy. So let's go on and implement it. Let me first connect the GGL slab between the node and the video plane. Okay, great. Then one thing we need to do is to basically get two textures. One is going to be the texture containing our image, so all the objects in our scene, and the other is a texture containing just the light. So in order to do that, and in case you don't need to have transparent objects, my preferred way of doing this is to actually set the alpha value to 1 only for the light. So let's set it actually to 1 here. Only for our light. So what happens when we go into GGL node here and we create a GGL pixel, right? So if we go here, let's actually switch only the alpha of this. Okay, cool. And you can see that actually our object has an alpha value of 0 apart from the diffuse light, which we're going to change in a second. And actually the background also should have an alpha value of 0. So let's go here and get only the first 3 components of the swatch, of the list we get from the swatch. So basically the red, green and blue, and let's set 0 for the alpha. Great. So now only the light and the diffuse part of the image have an alpha. So let's actually get this correctly. So matte diffuse, let's set it with an alpha of 0. Let's set also matte specular to an alpha of 0. Let's set also matte ambient to 000 and matte emission to 000. Great. So it's still not the alpha is still not set to 0 for some reason, because probably is the aux color. So let's check aux color. Let's set it to 1110. Okay, now the alpha is still set to 1 for the light. So what have I forgotten? And what I've forgotten is auto material 0. So we also need to give it auto material 0. So great, so now the only thing that has an alpha value of 1 in our scene is the light. As you can see, when the light goes behind the sphere, it actually disappears because it's covered by the sphere. Great. So let's do it like this. This will be our second output, and our first output will be the image as it comes. Great. And then actually the second output will be the image as it comes, so basically the color of the light multiplied by the alpha value. Great. So if we check this with a JIT-P window, we can see that we get only the light in this second texture. When we cover the light here, we can see that it actually disappears. Great. So what is actually going on with our sphere? Probably let's set a bit of math ambient to something like 0.2, and let's set it also on the light. So ambient 0.2, 0.2, 0.20. Great. Let's actually attach also GGL material to the sphere to have a better shading of this sphere. Go to node, and we attach it to the sphere, and we need to give it all this matte stuff that we gave to the sphere. We need to give it also to the GGL material in case we attach it to a sphere, because now it's the GGL material that actually decides the color of the sphere. So yeah, that's what we need to do. Okay, good. It seems to be working. Let's check if we still have only the light on our second texture. Yes. Okay, great. Let's change the color to something. Ah, nice. So now that we got these two textures, the second one can go inside the second input of our GGL slab. Great. Okay, now let's go inside our shader code. So I'm in GL3. This algorithm works as well in GL2, but I'm going to write the shader with a GL3 dialect, so you want to switch to GL3 to follow this tutorial. So let's remove the scale thing, we don't need it. Let's remove the position, no, the position and text color we actually need. So let's just remove the scale here. Model view projection matrix, let's leave it. So this is the default shader, right? The one that I'm modifying. Good. Position, text card, model view projection. Okay, this is all good. So one thing that we need is to get on our fragment shader the coordinates also for the second texture. So let's do like this. Let's add here another variable, call it textCord1, and so let's then assign it here on the main function of the vertex shader and say, okay, JIT textCord 0 and 1, and we need to get JIT texture matrix 1. And textCord is the same. We only get one textCord coming from the object, but we need to transform this for the different matrix. It's actually the same because they are the same matrix, but in case we decide to make the second texture smaller than the first one, then we need another matrix. So let's actually go here, texture matrix 0, copy it, create another matrix. So texture matrix 1, so texture 1 matrix. Let's copy these also here, and then let's create another uniform, so mat4 texture matrix 1, and this should be it for the vertex shader. Great. Now let's go on the GPU Gems book, because this algorithm I got from the GPU Gems book. So there is a detailed explanation of the effect, how it actually works. So what we're going to do is to go down until we get to the shader code. There's a bunch of formulas and a bunch of graphics that explain you how this thing works. So we're going to get to the shader code, we're going to copy it, going to go in our shader, and in the fragment shader, inside the main function, we're actually going to copy these exactly here. Now it's a one-liner, so it's all in one line. We got to put this back into multiple lines. So for every line there is actually a comment that explains you what it does. So great. This shader is written now in how is this called, HLSL, which is the shading language for DirectX programming API. So I'm going to transform this code into GLSL code. It's very easy actually. So first we are going to put this back in the original form. because on GPU gems is all on one line, as you saw. So great, suck, 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 almost finished. Okay, so this is it. This is the code for the shader as it comes from GPU gems. So as you can see, we already got actually a main function, so we can delete the first line. Alf2 is actually a vector 2, and this stuff we are going to modify in 1 second. Okay, great. We need to define a number of samples. So before going inside the main function, let's actually go here on a new line and say int num samples, and let's start with 200 iteration per every pixel. So for every pixel we will go through this for loop 200 times, which is a lot of calculations, but our GPUs can take that. Okay, great. Then we get to convert this alf3 into vec3 and return float color multiplied by exposure. Let's actually copy this and put it in our out color. It's going to be a vec4 which contains the color multiplied by the exposure. So instead of return, this is HLSL stuff, we just need to assign this variable, this result, to the variable out color, which, as you can see, is declared up here as an output variable, which goes to location 0, which means the color output of this shader. Okay, amazing. So what have I done? Let's put this graph parentheses back down here. Okay, great. So we need to create a bunch of parameters now, which are density, as you can see is written here, weight, decay, and exposure. So let's go all the way up here and start to create them. So param name. I always like to create my uniform variables with a U before of their name to remind ourselves that these are uniform variables. So for example, U exposure, this is going to be of type float, and by default it's going to have a value of 1.0, let's say. Great. Let's actually copy that line that we just wrote, go to a new line and create another uniform of the one containing the decay value. So we will see what these values do in 1 second. And let's give it a default value of 0.1997, which is something that I found to be working with the algorithm. So we need also the U weight. Great. Let's give it a default value of 1995. No, sorry, let's give it a default value of 004. Then we need the density as well. So instead of U decay, we write U density, and we give it a default value of 1995. Let's make them all nicely indented. Great. Okay, we need one more uniform value. And we need actually a couple uniform values still. So one is the size of the window. So we need to pass the window size to the shader, and we are going to do it using the state uniform called the viewport. So this is a state variable that Max provides to us. We don't have to input it as a uniform directly. We can just get it from the state of Max. So let's call it u window size, and this is going to be of type vec2 because contains two numbers, size x and size y, and let's give it a default value of 100 and 100, something like that. But not default, this is actually a state variable, so we have to write state, actually not caps lock, but minuscule, as it is written here. These are also state variables, the texture matrix 0 and the texture matrix 1, the position of the texture, this is all stuff that gets provided us by Max. While those uniform, we have to provide ourselves attaching some messages to the shader. Okay, so that's the difference between the state and the default. Great, then we need another one that is actually a uniform that we have to provide, so param name, which is the light position. So u light position, which is actually the light screen position, so the position of the light in the screen and not in actually in the world. So this is going to be of type vector2, default value, let's say 100. And I make a very big mistake here, because instead of writing the default values, which I actually copied wrong because I'm looking at my code here, I actually copied it wrong. This is actually viewport. We need to write viewport to say, okay, from which state you want to get those values, from the state called viewport. Okay, amazing. As you can see, all the state variables are written in caps lock. Okay, now we need to bind those variables. So let's actually start. We must bind all of them basically to the fragment shader. So fragment program, FP instead of BP. So U exposure, U decay, then U weight, exposure, decay, weight, density. Then we need the light screen position, and in the end the window size. So why all to the fragment shader? Because this algorithm is going to take place all inside the fragment shader. This is why we're using a slab object and not a GGL shader object. So let's go finally inside our fragment shader, and let's actually add this second text code input that we declared in the beginning. So text code 0 and text code 1. Because this is our output from the vertex shader here, Jitter vertex, which gets written here with those variables. And then we need to input it in the fragment shader with the same values inside. It must contain the same values. So this is a data structure that contains these two variables. Good. So let's get rid of this uniform float scale. We actually need also another texture, so let's go up here and declare it. This is going to be our texture one, the one containing the light. So let's actually name them like with the image texture. So this is going to be our the texture containing the image, the scene, and this is going to be the light texture, so the texture containing only the light. So let's actually pin them, also bind them. Image texture here, copy that, and write light texture. So, and this is the default value of 0, and this is the default value of 1. So this is the one that comes in the first input, and this is the one that comes in the second input of the GGL slab object. Great. So let's go down here and copy that. These are textures that have the rectangle 1 enabled. This is why we need to use the sampler to direct. So image texture and light texture. Amazing. Then we need to bind all these uniform that we created. So I'm just gonna copy them from my code that I already wrote, so I don't have to spend 1 hour writing them all by hand. So you will have to do that though. So uniform, oh actually I called them in a different way, so in the end I will have to spend some time. So instead of window size, I would wrote U window size. And instead of light pause screen, I call this U light screen pause. Okay. Then U exposure, U decay, U density, and U weight. Okay, great. So this is it. This is basically almost it. So let's change a couple of things inside our code. Instead of screen light pause, we write U light screen pause. Instead of text code, we need to create another variable here. It's a text code 2, so let's call it text code 0, and this is going to be equal to JIT in dot text code 0. So why are we creating another variable? In theory, we don't even need to do that. We could just use text code 0 here instead of text code. But in case we want to modify this variable, so the text coordinates, we need to do it in a new variable. We cannot modify an input variable, so we need to create a new one in case we want to modify that. I don't think this is gonna be modified, but just for the sake of it, we just create a new one. And then we do the same thing for text code 1, which I know that this we're going to modify. So let's create this here, git text code 1. So it's going to be text code 1. Great. Oh, here I forgot to put a vec3. This is actually going to be a function called texture in GLSL, and we're going to use the text code 0 for that. And as you can see, this is a vector tree, so we actually just want to get the RGB from this, this is going to be our image texture. So we are sampling here our image texture, and we just want to get the red, green, and blue. So why are we sampling the image texture here? Because we want to output it. So in GLSL, in a slab, in a fragment shader, if you want to have as an output a texture, you need to sample it and then output it. So alf becomes actually a float. Okay, great. Let's see if I forgot something else. Oh yeah, of course we need to now rename all the uniforms here with a U on front. So U decay, U exposure, and U weight, and here there is U density. Okay, so you need to put a U in front of these uniforms that we created. Now inside the for loop, we need to change this text to D into texture. Frame sampler, this is going to be our light texture. Exactly, which we declared up here, exactly. And text code, this is going to be text code 1, and this is going to be text code 1 as well. Okay, I think this could be it. This could be it. Let's go in our patch and see what we actually, not this one. And let's see actually what are we getting out of it. So we don't get anything, there's probably some errors. I think my max is probably crashing now, too much excitement. No, it managed not to crash, amazing. We stop the rendering process and see what's going on. It's a bit crashy. I know he wants to crash, it just doesn't manage to crash. Okay, we got a lot of errors, implicit cast. Okay, there is an implicit cast between back 4 and back 3 because I forgot here to put RGB. Because this is actually also a back 3, this sample here. And a texture returns always a back 4, so we actually need to put the docked RGB in GLSL. Maybe in HLSL it's different. Okay, cool, it actually works. It actually works. Our algorithm works. Now, what we need to do, let's first take a look at the algorithm and see how it works, and then we see how we finish this code. So maybe we will manage all of these in a single video. So, what's happening in this algorithm? First thing we do is to get the text code coordinates for these objects. So what are the text code coordinates? Basically, every one of those pixels in our texture has a coordinate. It's like just a grid with some coordinates, right? So these texture coordinates are something that gets passed from the vertex shader, gets multiplied by the texture matrix, which transforms those coordinates according to which texture comes in from the dimension of the texture and so on. Then we pass them out by putting them inside our out structure. We pass them out in the fragment shader. Good. Then there is this delta text code, as the comment says, calculate vector from pixel to light source in screen space. We calculate a vector that goes from the pixel to the light. So why from the pixel? Because if you remember from my other videos about vectors, if we subtract two vectors, the vector that is on the front of the subtraction is gonna be the head of the vectors. So the vector is always gonna to go in the direction of the head. So the vector is going to go, in this case, from the light to the pixels, okay? So this is the direction of these vectors. Okay, so we have a bunch of vectors, and this happens for every pixel inside the image, right? So for every pixel we have a vector that goes from the position of the light toward the pixel that is at the moment being worked on. Then we multiply this delta text code by 1 divided by the number of samples, which is this number here, multiplied by our variable density. So what does this mean? Basically we are dividing it by number of sample multiplied by density, right? So in this way we can make this vector smaller. So why do we need to make this smaller? Because this is going to sample, with this vector we are going to sample this image here, which means that for every iteration in this for loop, we are going to sample this image and bring it on some pixels farther using those vectors. So this is simply our image, the scene as it comes inside. We just sample it using the texture coordinates untouched. Cool, then we create a variable called illumination decay, and we assign it to 1. So this is the illumination decay factor. Good, then we go inside the for loop. So every time we go one iteration of this for loop, from the texture coordinates 1, which are the ones that are going to sample the texture with the light, we subtract the delta texture. So every time that we go in the loop, we subtract this vector. Okay, so then we sample the light texture using the new texture coordinates. So then we multiply this image that we got for our illumination decay, which is 1, multiplied by our weight, which is a uniform. And then we add the sample to our original image. So we just add the light ray to our image. And then we multiply this illumination decay by our decay, which is another uniform, so it gets smaller and smaller for every iteration of this for loop. So just to clarify how this algorithm works, I have implemented it again quickly inside the GGLPix, which is also a valid option. Actually, we could have implemented it completely in GGLPix, it would have worked exactly the same way. I will add this patch to the Patreon download. So anyway, I want really that it's clear how this algorithm works. So let's examine it once more. So what it does exactly, let's say that we are at this pixel here, we are working on this pixel here, so our GPU is at the moment examining this pixel here, and our light position is here, okay? So we're working on this pixel here. So this pixel here gets subtracted the delta texture. Now the delta texture we saw is just the vector that goes from this pixel, actually from the position of the light, and then the delta texture gets divided by the number of iterations multiplied by our density factor. So this means that if we make the density factor 1, this delta texture will be exactly 1/29th of the vector that goes from the pixel to our light position. Okay, great. So every time that we go in the for loop from this pixel, we advance one little piece from the pixel in the direction of the light position. Okay, so this means that now the pixel here is adding to the color a sample taken at 1/29th distance from the sample and the light. Then in the next iteration of the for loop, it will take another little step toward the light, then another one, then another one, then another one, until it finds actually this image, and then it adds this color white. That's why here is so dark, the color, because it didn't find many white pixels to add to the current color of this pixel. And then it goes on to the light position, but it doesn't find anything. And the same works for every pixel inside this image. For example, if we put the light here on the center, the delta texture will go from every pixel toward the light position, and every little step which will basically bring the pixel toward the light position. If we make the density bigger than 1, it means that actually these steps will be smaller. That's why the rays get smaller. But it's important to understand that this for loop, it's only adding this color to the single pixel. It's not adding the colors to the subsequent pixel. It's only working on this pixel. So if we make less iteration, what we're gonna have is simply a lower resolution rays, because we are not adding so many colors to the single pixels. So that's actually how this algorithm works. Hope this was clear enough. Cool. Then in the end we just output our color, so which is the color plus all the rays summed, multiplied by the exposure, which is simply a multiplier for the final image. Okay, great. So one thing that we just missed from in our patch actually is to get the light position into screen space. Because if we get just the position of the light, this is going to be in world space. So if we do something like this, get position, or actually we just use those values as the position of the light, this is just going to be in world space. So what we need to do is to send this message to the JIT world, and to send these coordinates to the JIT world, prepend by the word send render, because this is a message for the render inside the JIT world, and then world to screen, and 1 and 2 and 3. Now we actually want to get 2 and 3 and 4, because the first is going to be the word position. Okay, great. So because once we do this, oh, of course now it thinks we want to move this message there. So let's actually say root position Otherwise the message will just go to the position indicated by those numbers. Good. And then let's say $1, $2, $3. Okay, great. So when we move this, we will get the position of this object in screen space. Okay, so this is the values we got assigned to the shader. Now the problem is that when we move the camera, the position of this object in screen space changes as well. So we actually need to get this position every time we move the camera. So let's actually go here and say root world to screen from the JIT world. So if we manually change this position, we should get exactly the position in screen. But if we move the camera, this is not gonna happen. So one thing to make this happen, so for example, let's actually receive the metro here and continuously bang this list. Okay, but the position is not changing even if we move the camera. Moving the camera with the WASD keys on my keyboard using the Jitter drive, as you already know from my other videos. Okay, great. So, but as you can see, the position is not changing. So what we need to do for this to happen... Okay, so actually instead of sending a metro here to the send render message, let's actually send a metro to a get position message that we will send to the GGL grid shape. So we will get the position here where we change it exactly. Good. So then let's say root position. So we get only our position. And let's send, oh, I actually already had it. And let's send this to the JIT world. Okay, good. So now, as you can see, when I move the camera around, the position of the light in the screen is not adjusted for the new position, actually. It's always related to the last position that we gave it when we manually moved those numbers. So in order to do this, there is a strange thing that we need to do, which is to give both to the camera and the JIT world to draw both of those objects to a fictionary context. Don't ask me why, but this is how it goes. So why can I actually not do that? I'm really trying to write it here. Oh, okay, the book was pressing on my keyboard, I get it. Okay, so both the world and the camera now draw to the fictionary context called JIT, called the JITX, and as you can see now, when I move my camera around, the position of the light in the screen is changing automatically. So a little trick for you guys, if you were asking yourself how to do that, that's how you do it. You draw the camera and the world both to a fictionary context, and then when you move the camera, the world is going to give you the new position adjusted to the screen. Great, so how did we actually call this uniform here? ULight screen pos. Okay, great. So let's go here and say prepend ULight screen pos. So we can finally now use those numbers and pass them to our shader. We actually are interested only in the first two numbers because this is a screen position. So only X and Y. Let's pass those to the shader and let's see what we get. Oh, it's wrong because we need to say param. This is a parameter. So param. Good, good. So, okay, it's not working perfectly. Let's see why. Let's actually get like a floor in order to have a sense of what the hell we are going. So GGL grid shape, it's going to draw to node, shape plane, scale 5, rotate XY 9000. So if we just leave it like that, you can see that it actually gets taken inside our algorithm, which is a pretty cool effect, but probably it's not what we want. So in order to remove this from the effect, so not use it as a light, we need to give it a color of whatever color we want with the alpha value of 0. Exactly, let's position it a bit down, so 0, -1, 0. Let's give it a color of like reddish something. Well, something like that. Okay, great. Let's actually also enable the light just for fun, or let's actually attach GGL material to it, but then we need to rotate it the other way around. Okay, great. So there we go. Okay, the light, the algorithm is not working perfectly. Let's see why this is the case. Oh yeah, I remember now. One thing that I found out is that we actually need to reverse the y coordinate in order for this to work. That's why we were actually input the window size, which if you are really attent, you will have noticed that we didn't use yet. So we need to do something like this. We need to create a vector 2 here with textcore.x, and then we need to go with u window size.y minus textcore 0.y. Don't ask me why we need to reverse the y coordinates. I don't know exactly. I think this is just because the coordinates in HLSL are the other way around. That's why the algorithm is written as it's written. So great, let's see if this actually works. Okay. Okay, this I found out as well. One other thing that we need to do then, once we do that, is actually to reverse the y coordinates again. So delta car.y multiplied by minus 1.0, because this is just to reverse it. So if this was like going like this from 0 to 1, now it will go like this. 1 will be on the top and 0 will be like here. But now that this goes from minus 0 point whatever to whatever, then we actually need to multiply it by minus 1 in order to get the correct behavior. And in fact, we just got it. Amazing. So once the light is behind the shape, we don't see any rays. And when the light comes out from the shape, then we see the rays, whatever. So amazing. Let's just change the color of the light. So like this, let's say prepend diffuse for the light. Actually doesn't matter if we set the alpha to 1 for the light, I believe. Just try. Exactly. Let's change also the color of the shape. Prepend color. Amazing. Yeah, this is it. Here is our nice sunset light. Okay, so now let's create our uniforms in order to modify the parameters for the shader. Actually, don't need this second input here inside GGLPix. So what do we got? We got param u decay. Let me actually copy them. I already wrote them here. So there they are. So the exposure, we say, is just a multiplier for the whole scene, right? So we can leave it to 1. The density, as we saw, the density is a multiplier for the divider of the delta texture coordinate. So the bigger is the density, the smaller will be the delta between the texture coordinates, and we can actually see the different stages of the sampling if we make it very big. So we want to keep it below 1, let's say, around 0.9 and 1, depends how much. So if we just keep it to 0 basically, or to a number close to 0, we are just sampling the light image as it is, and if we make it bigger, we're basically sampling farther away from the original image. Great, so it's basically how long the rays are. Then the decay is basically how fast the light is going to decay. So we probably want to keep it around also 0.9 or something like this. Cool. Depends how strong you want the light to be. And then the weight is basically the weight of every sample. So this is also kind of a multiplier of the ray's amplitude. Okay, so let's try to move up and down our light. Okay. Yeah, it's really cool. Now, this algorithm has a lot of problems which will you surely discover yourself, like basically that if the light is behind an object, we don't see the light at all, the light rays at all, when I would actually expect to keep on seeing the rays coming out from behind the object. So this could be seen more like kind of an effect caused on the lens of the camera, but we can still achieve very nice result. You can also kind of trick the algorithm and just create objects that are actually emitting lights. So for example, if you will just create a sphere that emits light like that. Okay, a sphere is a bit crazy, but you get the idea. You can actually emit light from whatever. You can emit rays from whatever object you want. So yeah, it's really cool. It really adds a lot to a scene, and I expect to improve this algorithm in the future, or to change algorithm for volumetric light to a different one. This is just the most basic one that you can find on GPU Gems. Volume 3, so there it is, the algorithm, developer, nvidia.com, GPU Gems, Volume 3. It's very funny to try to convert those algorithms into Max, the shader code. So I think I will do more videos about this in the future, so this could be actually the first of a series. Okay, I think this is enough. Thank you very much for following. If you have questions, please join my Patreon and ask me them on Discord, because otherwise I will definitely forget. So yeah, check my Patreon and download this patch. It will be available for my patrons right now, for everybody else in 1 week, as always. And most of all, thank you very much for following me in this rambling of about half an hour, I believe it is now, maybe more. So thank you very much, and see you soon in the next video. Ciao, ciao.